Dear students, in previous class we were discussing about the order properties of arrays. So now let us discuss the another property. So that's also familiar. If a greater than 0, then 1 by a is also greater than 0. If a is positive, then 1 by a positive. Similarly, if a is negative, 1 by a is also negative. That's immediate. The proof is immediate. Why? Suppose it is given. If a is positive, then surely a differs from 0. Therefore, 1 by a exists. Okay. So if 1 by a positive and if 1 by a is negative, what happens here? If possible, 1 by a is negative, then we have a into 1 by a. A into 1 by a positive, 1 by a negative, means a into 1 by a equals 1, which is negative. That's a contradiction. This contradiction is due to our wrong assumption, hence 1 by a is positive. So when a is positive, 1 by a is positive. By the similar arguments, we can show that when a is negative, 1 by a is also negative. Okay. Now consider another result. If a and b are any two real numbers, then a less than a plus b by 2 less than b. So this a plus b by 2 is known as actually the arithmetic mean between this a and b. A plus b by 2 is the arithmetic mean between a and b. So how to prove this one? A and b are following R with the a less than b. Consider these two conditions. If a and b are real numbers with the a less than b, then the arithmetic mean between a and b is a plus b by 2. So it lies in between this a and b itself. It is given a less than b. Okay. A less than b means it is surely for any real number a. So a plus a less than b plus a. If you add a on both sides, so it is a plus a less than b plus a. A plus a less than b plus a means here 2a less than, that means 2a less than a plus b, that means a less than a plus b by 2. Agree? A less than b plus, sorry, a plus b by 2. Again, a less than b, so that means a plus b less than b plus b. Add a b on right side, both sides. That means a plus b by 2 strictly less than b. So clearly a less than a plus b by 2 and a plus b by 2 less than b. So combines we have a less than a plus b by 2 less than b. So this a plus b by 2 is the arithmetic mean between a and b. Okay. Now consider another interesting result. Suppose a is any real number. A is a real number. With the epsilon is any positive quantity. What is epsilon? Epsilon is a sufficiently small positive quantity. Then if 0 less than or equals a less than epsilon, this implies a equals 0. 0 less than or equals a less than epsilon. For all epsilon is positive, then a equals 0. That's our requirement. So listen. 0 less than or equals a less than epsilon. A is a real number. When a equals 0, nothing to show. If a differs from 0, suppose a differs from 0. Since a differs from 0, then clearly a should be positive. Why? Because 0 less than or equals a. It is given 0 less than or equals a. So when a is differs from 0, then 0 strictly less than a. That means a is positive. When a is positive, surely a by 2 strictly less than a itself. For any positive quantity a, for any positive number a by 2 strictly less than a. Put on epsilon is a by 2. So come to the choice of epsilon. What is epsilon? Epsilon is positive. Since a is positive, a by 2 is also positive. So you can choose epsilon as a by 2. Then we have it is 0 less than epsilon less than a by 2. Why? Because a by 2 less than a. So 0 less than, since a is positive, or 0 less than a means 0 less than a by 2 also. A greater than 0, a by 2 is also greater than 0. So here 0 less than epsilon less than, or sorry, so it is 0 less than a by 2 less than a. So a by 2 less than a means 0 less than a by 2 less than a. Put a by 2 is epsilon, so it is 0 less than epsilon less than a. That's a contradiction to the choice of given condition. Therefore, this contradiction is due to our wrong assumption. Therefore, a equals 0. Clear? We have to show that when 0 less than or equals a less than epsilon, for epsilon on epsilon is positive. When a is 0, nothing to show. When a is differs from 0, clearly a greater than 0, that is given. Since a greater than 0, a by 2 less than a itself. Therefore 0 less than a by 2 less than a. By the choice of epsilon, we know that epsilon is a positive quantity. Since a is positive, a by 2 is positive. So you can choose epsilon as a by 2. So according to this argument, we have 0 less than epsilon less than a. But it is given 0 less than a less than epsilon. So this statement, the obtained statement, is a contradiction to the hypothesis. Thus clearly this contradiction is due to our wrong assumption. Therefore a should be 0 itself. Okay. So these are some important properties, but all of these are familiar with you. Okay. Now determine the set A of, before going to that one, if AB is positive, A and B are editorials, AB is positive, then either A positive and B positive, or A negative and B negative. AB is positive, then either A positive or B and B positive, or A negative and B negative. How to prove? It is given AB is positive. AB greater than 0. Let A is positive. Consider A positive. Then to show that B greater than 0. Since A is positive, surely A is positive, we have A differs from 0. Since A is positive, A differs from 0. A differs from 0 means 1 by A exists. Okay. Since A is positive, surely 1 by A is positive. Already this result is obtained. So now let B. What is B? B equals B into 1. That equals B into 1 means A into 1 by A equals AB into 1 by A. Okay, associate this. But what is AB? AB positive. What is 1 by A? Positive. So this should be greater than 0. Why? Because AB is positive. Because AB is positive and 1 by A is positive. Therefore, sure it is given, or we have it is B is positive. When A is positive, AB is positive, and if A is positive, then B is positive. Similarly, if A is negative, then again 1 by A exists, also 1 by A is negative. Then what is B? B equals, it is B into A into 1 by A, that is, yes, it is A is negative, and B means B into 1 by A, so it is AB into 1 by A. AB is positive and 1 by A is negative, so it is negative. So when A is negative, B is also negative. Okay. Similarly, if AB is negative, AB negative means either A negative and B positive, or A positive and B negative. You can prove that result by the same argument. Agree? Now, consider the problem. Determine the set of all real numbers. Determine the set of all real numbers such that x square plus x greater than 2. X square plus x greater than 2. Determine the set of all reals such that x square plus x greater than 2. Let A equals set of all x of all in R such that x square plus x greater than 2. X square plus x greater than 2 means x square plus x minus 2 greater than 0. That means that equals set of all x of all in R such that x square plus x minus 2 means it is x plus 2 into x minus 1 that should be greater than 0. Okay. That means it is set of all x of all in R such that AB positive means both A and B are positive. Therefore, it is clearly it is x plus 2. Then there are two possibilities. X plus 2 into x minus 1 is positive. Then either x plus 2 into x plus 2 positive and x minus 1 positive. Okay. Or x plus 2 is negative and x minus 1 is negative. Why? Because we know that when AB is positive, we already proved this result. When AB is positive, either A positive and B positive or A negative and B negative. So, x plus 2 positive and x minus 1 positive. X plus 2 is positive means x greater than minus 2 and x greater than 1. X greater than minus 2 and x greater than 1. Here it is x less than minus 2 and x less than 1. Okay. Means come to the number line. So here x greater than minus 2 and x greater than 1. This satisfies only when x greater than minus 2 and x greater than 1. So here x greater than minus 2 and x greater than 1. X minus 2 and x greater than 1 means, so if you choose x is minus 1, it is not satisfied x greater than 1. So this is the shaded field or the shaded area is our region. If you consider here, consider the real line and consider the real line. It is x less than minus 2. X less than minus 2 means this one. And x less than 1 means this one. So here the required region is this shaded region. Okay. Therefore, what is A? Thus A equals set of all x of all in R such that x greater than minus 2 and x greater than 1. So it is x greater than 1. Or means it is union. Set of all x of all in R such that x less than minus 2 and x less than 1 means x less than minus 2. So this is the required region. Okay. So this is the method to find out the solution of these types of problems. Set of all, so x square plus x greater than 2. Then its solution is set of all x of all in R such that x greater than 1. Union set of all x of all in R such that x less than minus 2. Agreed. Similarly, consider another one. Suppose consider another problem. Determine the set of all real numbers such that 2x plus 1 by x plus 2 less than 1. Determine set of all real such that 2x plus 1 by x plus 2 less than 1. How? So let A equals set of all x of all in R such that 2x plus 1 by x plus 2 strictly less than 1. That means A equals set of all x of all in R such that it is 2x plus 1 less than x plus 2. That means A equals set of all x of all in R such that it is 2x plus 1 less than x plus 2 means bring x to the left side. What you get? It is x. 2x minus x. X less than 2 minus 1 means set of all x of all in R such that is x less than 1, or means x minus 1, it is it is a set of all x of all in R such that 2x plus 1 by x plus 2 is less than 1. Okay, that means set of all x of all in R such that 2x plus 1 by x plus 2 minus 1 is negative. Okay, that means it is set of all x of all in R such that it is 2x plus 1 minus of x plus 2 on divided by x plus 2 strictly negative. Okay, so that means set of all x of all in R such that 2x plus 1 minus x plus 2, 2x minus x. So it is x minus 1 by x plus 2 is negative. X minus 1 by x plus 2 is negative. Set of all x of all in R such that x minus 1 by x plus 2 is negative. Then we know that a by b is negative when either a negative and b positive, or a positive and b negative. Okay, so here it is x minus 1 is positive and x plus 2 is negative, or x minus 1 is positive and x minus 1 is negative and x plus 2 is positive. Why? Because of the nature of this a by b. Okay, x minus 1 greater than 0 and x plus 2 less than 0 means it is x greater than 1 and x less than minus 2, or it is x less than 1 and x greater than minus 2. Okay, x less than 1 and x greater than minus 2, or x greater than 1 and x less than minus 2. So combines, then it is nothing but a equals set of all x of all in R such that minus 2 less than x less than 1. Okay, so this is the set of all reals which satisfies this condition. Clear? Okay. Now, consider another result. Let A and B are positives, or A and B are any two reals. A greater than or equal to 0. If A greater than or equal to 0 and B greater than or equal to 0, then we have A less than or equals B implies and is implied by A square less than or equals B square. Okay. Also it is implies and is implied by root A less than or equals to. So these are familiar results and the proof is so immediate. Okay. So what about the relation between the geometric mean and the arithmetic mean between any two real numbers? That's our next task. We know that the geometric mean always less than or equals its arithmetic mean. GM less than or equals A. If A and B are any two reals, then GM less than or equals A. The geometric mean between any two reals less than or equals its arithmetic mean. How to prove this one? And whenever the equality holds if and only if A equals B. What is the geometric mean between any two reals? It is root AB. What is the arithmetic mean between any two reals? A plus B by 2. So it is root AB less than or equals A plus B by 2. Okay. Now listen. If A and B are zeros, nothing to do. Okay. So if A differs from 0 and B differs from 0, if A and B are reals, nothing to show. The equality holds the immediate. If A and B are differs from 0, also A differs from B. A differs from B. If A differs from B, then root A differs from root B. Clear? Root A differs from root B means root A minus root B differs from 0. Okay. Root A minus root B differs from 0 means root A minus root B, the whole square should always positive, since it is differs from 0. So root A minus root B whole square greater than 0 means what is root a whole minus root b whole square? It is a plus b minus 2 root ab, that is should be positive. So that means a plus b by 2 strictly greater than root ab. So that means root ab strictly less than a plus b by 2. So the strict inequality holds. Now, what about the equality? Consider the equality if root AB equals a plus b by 2. What you get? It is that implies 2 root AB equals a plus b. This implies and is implied by 4AB equals a square plus b square plus 2ab if you squaring on both sides. So 4ab equals a plus b whole square, that is this one. That means 0 equals a square plus b square minus 2ab. Bring 4ab to the right side. So that means it is 0 equals a minus b whole square. A minus b whole square equals 0 means a equals b, or a minus b equals 0. A minus b equals 0, that means it is a equals b, so equality holds. Okay, so from here we can conclude that gm always less than or equals a. So we can generalize this result. If a1, a2, etc. an are any n real numbers, then a1, a2, etc. an all power 1 by n, it is less than or equals a1 plus a2 plus etc. plus an all divided by n. So this is the generalization of this result. If a1, a2, etc. an are any n reals, then a1, a2, etc. an all power 1 by n less than or equals a1 plus etc. plus an by n. Okay, the equality holds. Equality holds only when a1 equals a2 equals etc. equals a. Clear? Thank you.